Hello. In the last lecture, we have learned about quasi-isometries and Cayley graphs of finitely generated groups. In this lecture, we'll prove the following lemma, which is called Swark-Milnor lemma. So it says the following. So if a group, if it acts properly and co-compactly by isometries on a proper geodesic metric space, so then that group is finitely generated and the Cayley graph of that group is quasi-isometric to that geodesic metric space. Let us begin with the definition of proper action. So let X be a geodesic metric space. An action of a group on this metric space X is said to be proper if for all elements X and for all positive number R, the set consisting of all group elements G such that the G of this closed ball around X of radius R intersection the closed ball around X of radius R, if it is non-empty, so this set is finite. So the set of translations of this closed ball which intersect this closed ball around X, so that set of translation is finite. So then we call this action of this group on this metric space X to be proper. And what is the definition of co-compact action? So this already we have seen. An action of a group G on a metric space X is said to be co-compact if there exists a compact set K such that the union of the translates of this K is equal to X. So union of GK, where G belongs to this group G, is equal to X. Now let me state what is Swark-Milnor lemma. So let X be a geodesic metric space. If a group G acts properly and co-compactly by isometries on X, then this G is finitely generated group, and this orbit map G from to X, so G to X, so G is going to this small element, G is going to G dot X naught. So this map is a quasi-isometry. So in fact, this map you can extend it to Cayley graph naturally, and that map will be a quasi-isometry once you prove that this map is a quasi-isometry. Okay, so let us begin with the proof. So you know that this action is a co-compact action. So there exists a compact set K such that union of these translates of this K is equal to the metric space X. Now let us take some point X naught belongs to this metric space X. So there exists a positive number capital D such that so this K will be contained in this closed ball around X naught of radius capital D. So this is because this K is compact. So therefore this K will be bounded. Okay. So now let us take this set S to be the all elements of this group G such that so this translate of this closed ball of radius 3D around X naught intersect the closed ball around X naught of radius 3D. So this is my set S, and because this action is proper, so this S will be a finite set. So what will show that So this set S, in fact, it is a generating set of G. And because S is a finite set, so therefore this G, it will be a finitely generated group. Okay. So now let us take an element small g from this group capital G, and let us take alpha to be a geodesic in X from X naught to Gx naught. Yeah, so alpha is a geodesic from this X naught to Gx naught. So in this definition of this alpha, so dxy, it should be dx naught, and y should be Gx naught. So alpha, it is a map from this closed interval 0 comma dx naught to Gx naught to X. So alpha is a geodesic joining this X naught and Gx naught. So this is my geodesic alpha. Okay. So now what you do, so now you consider the following partition. Of this closed interval 0 to distance between X naught, Gx naught. So you take this partition T0, T1, Tn such that distance between alpha Ti minus 1 and alpha Ti is equal to D for I equals to 1 to n minus 1, and distance between alpha Tn minus 1 and alpha Tn is less than equals to D. So this always you can do. So in the picture, so this is my alpha T1. So here in this geodesic, we'll get alpha Ti minus 1 and alpha Ti. So this distance, so this will be exactly equal to D. And this I is varying from 1 to n minus 1. And in the last segment, so this distance, it will be less than equals to D. So now let us take Yi to be equal to alpha Ti, and let us take Gn to be equal to G. Now, so this X, so this is the union of the translate of this balls around X naught of radius D. So why this is true? So we know that X is equal to union of the translates of the compact set K, and K is contained in this closed ball around X naught of radius D. So therefore, so X will be equal to union of translates of this closed ball around X naught of radius D. So now note that because of this, so there exists Gi in this group G such that distance between Yi and Gi X naught, it will be less than equals to D. So it follows from here. So we have this point yi, and for this point I'll get a orbit point gi x naught such that the distance between yi and gi x naught is less than equals to d. So now observed by triangle inequality, distance between x naught and g1 x naught is less than equals to 2d. So distance between this x naught and g1 x naught will be less than equals to d plus d, which is equal to 2d. Distance between g1 x naught and g2 x naught, it will be less than equals to d plus d plus d, will be equal to 3e. So distance between g1 x naught and g2 x naught is less than equals to 3d, and this group is acting by isometry. So therefore distance between x naught and g1 inverse g2 x naught will be less than equals to 3d. So this will imply that this element, group element g1 inverse g2, it belongs to S. Similarly, for this I, which is less than equals to less than n, so distance between gi minus 1 x naught and gi x naught will be less than equals to 3d. So distance between x naught and gi minus 1 inverse gi x naught will be less than equals to 3d. So this will imply that the group element gi minus 1 inverse gi will belong to this set S. And when I is equal to n, so distance between gn minus 1 x naught and gn n x naught will be less than equals to 2d. So this will imply that this group element gn minus 1 inverse gn, it belongs to S. Now we have started with a group element G, which is equal to Gn. So this Gn can be written in this following way: G1 multiplied by G1 inverse G2 multiplied by G2 inverse G3, like this. And each of this element, so this G1 inverse G2, G2 inverse G3, so they all belong to S. So G1 also, it belongs to S. So therefore, so this group G, it is generated by the set S. So G belongs to the group generated by S, which is equal to this group G. Okay, so G is generated by S, as S is finite, so G is finitely generated group. Now we want to prove that this group G is quasi-isometric to the space X. So now observe that, so distance between x naught and gx naught is equal to n minus 1 times d plus epsilon, where epsilon is greater than equals to 0 and less than equals to d. So it follows from the partition what we have chosen. So the way we have chosen the partition, it follows from there. Okay. Also, we have seen this thing. So G is equal to S1, S2, Sn, where S1 is equal to G1 and Si is equal to Gi minus 1 inverse Gi. Now the distance between this 1 and G in this group G will be less than equals to length of this element G, and length of this element is exactly equal to n. It follows from here. So now distance between this x naught and g x naught, so this is equal to n minus 1 times d plus epsilon, and n is greater than equals to distance between 1 and g in the group capital G. So this will be greater than equals to distance between 1 and g minus 1 times d plus epsilon. So therefore we have this thing here. So this inequality we have. Now if G is equal to A1, A2, AM, which represents the geodesic word, means length of this G, it will be equal to the distance between 1 and G in the group. So the distance between 1 and G, so this will be equal to M, because this G, this word, it represents the geodesic word. So now let us take the distance between x naught and gx naught. So this is equal to distance between x naught and the element a1, a2, am x naught. So now we just apply this triangle inequality. So this distance, so this will be less than equals to distance between x naught to a1 x naught plus the distance between a1 x naught to a1 a2 x naught. And you can continue in this way, and at last we'll get distance between a1 am minus 1 x naught and a1 am x naught. So now observe that, so distance between a1 x naught and a1 a2 x naught is exactly equal to the distance between x naught and a2 x naught, because this group is acting by isometry. So this distance, it will be equal to distance between x naught, a2 x naught, and this distance, so this will be equal to distance between x naught and am x naught. Now let us take r to be the maximum of the distance between x naught and ax naught, where this a, it belongs to this set S. So S is a finite set. So therefore, so what we got, so distance between x naught and gx naught, so this will be less than equals to m times capital R. And this m, it is nothing but the distance between 1 and g. So therefore, what we have proved, so if I take two elements, g and g prime belongs to this capital G, and g is equal to g inverse g prime, so there is one typo here. So let us take this to be g double prime, this to be g double prime, or let us do in this way. Let us take g prime and g double prime, two elements in this group capital G, and g is equal to g prime inverse g double prime. So distance between this 1 and g in the group will be equal to the distance between g prime and g double prime, and distance between G prime and G double prime x naught. So this will be equal to distance between x naught and G prime inverse G double prime x naught. So from the equations 1 and 2, so what we'll get? So d times the distance between G prime and G double prime minus d minus epsilon will be less than equals to distance between G prime x naught G double prime x naught, and that is less than equals to distance between these two group elements in the group G. So from this inequality, it is clear that so this map from G to X, G going to G x naught is a quasi-isometric. Okay, so I'll stop here. In the next class, we'll learn about quasi-geodesics, and we'll prove that in a hyperbolic metric space, if I take a geodesic and a quasi-geodesic joining the endpoints of that geodesic, then they lie in a uniformly bounded neighborhood of each other. So that property is called stability of quasi-geodesic.